Ladies and gentlemen, a very good evening to all of you, and welcome to tonight's public lecture organized by the Mechanical Engineering Sectional Committee of the IESL. Tonight's topic is on the most abundant element in the universe. It's a source of energy, a precursor to life, and it's what powers the sun. Sri Lanka, to be hydrogen ready by 2030, will cover hydrogen generation in Sri Lanka, as well as the challenges we may face. This lecture will be presented by a true mechanical engineer with competencies in almost every aspect of engineering. He's a graduate from the University of Moratuwa and has decades worth of experience in overseas and local projects, in planning and implementing power projects, such as the Dendro Power Project, the Ambevela Wind Project, and the Amelipitia Diesel Power Plant, to name a few. Currently, is seeking new technology for the power sector and is actively engaged with global institutions to develop hydrogen power systems in Sri Lanka. He currently serves as a council member of the IESL and is registered as an international professional engineer in Australia as well as Sri Lanka. So please put your hands together for our distinguished speaker tonight, the chairman of the Mechanical Engineering Sectional Committee, Engineer Ruwan Nagawat.
Thank you. Thank you very much, Kanushika, for very elaborative description. And thank you very much all the members who had gathered here to listen about the hydrogen future in Sri Lanka. So generally on this topic, I would like to touch what we can do as a small nation. I don't want it to go into very big concepts, right? So main topic is to see how we can develop our own indigenous hydrogen system and to tell you what had been already taken place in the industry in this field. So if I go to the main part, so the hydrogen concept was generated by a French science fiction writer. So Jules Verne was he's like Arthur C. Clarke. He had predicted the water or the elements of water will be source of energy for the future. So this was 150 years ago, right? He had predicted this one. So his concept is becoming a reality now. So this novel he had wrote is The Mysterious Island. So on that one, the first concept of hydrogen was generated to the world, right? So we will go into the hydrogen. So we all know hydrogen is the smallest atom and it's the starting element in our periodical table, right? So it was discovered by Henry Cavendish, and the atomic mass, the structure, crystal structure, so everything is there. So the main problem is again for hydrogen is the nature of the size of the atom. It's very difficult to contain. It's the smallest atom in the universe. So being hydrogen, nobody will accept hydrogen as a fuel. So it need to fulfill certain characteristics for commercial world to accept it. So I had list out some of the characteristics that is required for any energy to be considered as suitable fuel. First one is the energy content. You can see there are many energy sources like geothermal, but the energy content you can harness is quite low because there's no exergy difference on that one. And Then the availability. You take again the geothermal, it is available only on few places. But if it is available around the globe, so it can be considered. The third one is engineering sophistication. For example, you take nuclear energy. How difficult it is to generate nuclear energy. So people would like to see simplest technology to have the conversion of energy from the fuel source. And fourth is cost of production. So it is the most vital factor. Even I listed as number 4. Everybody will look at the cost and the stage of development of energy conversion devices, right? So you can have an energy source, but if you don't have a conversion devices to utilize, you can't do it. So we have to see what would be the equipment developed to harness the energy and ability to handle fuel with safety. So we all know, even we take nuclear, it's very difficult to handle, right? So the safety concerns are very high, right? So we have to see when it is coming to the public domain, what would be the safety? And finally, the environmental impact of harvesting the fuel and fuel emissions, right? So you have fuels which will have higher environmental impacts when you're extracting, and also when you are using, again you have another impact. So we have to see all this one. So I will go one by one on this one to show why hydrogen qualify for this one. So you can see the hydrogen energy content. It's 141 megajoules per kilojoule. So we all know the gasoline, diesel, you can see it is 47. This is almost 3 times of the diesel or petrol. So it qualify, right? So it is having almost 3 times energy requirement than the fuels that we use today. So hydrogen will qualify on that matter. Then availability of hydrogen. So I will show you little clip on that one. Sound is not coming.
Speaker on, I think.
The energy spectrum, we would cease to exist. What causes this nuclear? The sun is the sole originating point of the event horizon of the system and our living Earth. Without its continuous nuclear fusion reaction, which we receive energy through the solar energy spectrum, we would cease to exist. What causes this nuclear chain reaction is fusion of hydrogen, which is also one of the main elements found abundantly in our atmosphere, but is mostly combined with other elements, similar to water molecules. Hydrogen is a renewable source, which can vector the present energy sources as a clean or renewable energy source derived from solar radiation, a resource that we are only now beginning to harvest.
So as it explained, hydrogen is the most abundant fuel in the universe, not only in our world, right? So everywhere you can see, even you take our world. So if you take water, you have hydrogen. If you take trees, plants, anything, it's made out of some hydrogen is joined in some form there. So it is the most abundant fuel in the world. where any country can utilize. It's not like a fossil fuel where few countries can dominate. So you will be able to use it any part of the globe, this fuel. So that is very important, right? So hydrogen passed that test also. Then the engineering sophistication of extraction the fuel. This is what we had done during our O-level and A-level classes. You might be remember, right? We will be popping up a balloon and sending the balloon out. So during our time, so the technology of extracting hydrogen was not a rocket science. It had been there. So we had been trying to do that. And also we try to put the match, right? And burn this one and see. When I was young, we all try to do that. So we know that the hydrogen, right, extraction can be done very easily, right? But we have to see whether this is commercially viable. It's a different scenario. But generally, generating hydrogen from whatever forms that it is, connected in the universe can be easily done, right? So hydrogen would qualify under this one also. The extraction technology is quite simple. And other one is the cost of production. You can see right now, 2020, the hydrogen was like per kilogram, USD 6 to 3, it varies on that one. So it is on a decreasing trend. By 2030, somewhere around, so that we will have the hydrogen in 2.5. So it will be on 2.5 to $4 range. But you have to see here, you will be paying $4 for 3 times the energy contents of diesel, 3 times the energy content of, that means 3 liters of petrol equal to $4, right? So that's the scenario we have to see. It is not kilogram to kilogram. You saw the energy content of hydrogen is 3 times higher, right? So even we pay higher amount, right, we will get the necessary energy at a very reasonable cost, right? So the cost factor is also coming down. So we will be having good competitive price. So the affordable price for everybody in par with other fossil fuels. Right. So the development of energy conversion devices. You can see right now the hydrogen car is already developed and testing. This is the hydrogen gas turbine. You can see with the main gas turbines, this is tested right now, testing at Airbus, France. So they are already testing this one, right? So, and there are liquid hydrogen powered ships, right? So all the technology, the conversion devices are on the test phase right now. So we are in a good ground where we can utilize. If we generate enough hydrogen, we will be able to convert or the use with the equipment, right? So other one would be the ability to handle the fuel with safety, right? So the major problem with hydrogen was, as I told you, hydrogen is a smaller atom. It will leak through any small, the cavities available. So it's very difficult to contain. But world has developed technologies, and so right now you have this fiber reinforced, carbon fiber reinforced canisters like this one, where it can withstand even bullets, sniper bullet, they can withstand. So it won't explode. So all the storage techniques has been developed so far. So the fuel can be easily stored and used safely. So the hydrogen pass on that part also. Then the environmental aspect. We know generally we look at the carbon dioxide emission of fuel. You can see all others, how many LBs they are issuing. Hydrogen, because you get water at the burning, right? So it is having the zero impact on the carbon dioxide emission or the global warming gas emission in the world. So it will qualify under that one. So I could say it's like orange tree. It's hydrogen is full with everything, right? So it passes all the energy content, everything. So this is like a wonderful. Every energy content wise, environmental friendly, accessibility, everything is, it's linked with hydrogen. So with that short note, I wanted to go into the session. So highlight of the session is I wanted to discuss the global fossil usage in transport sector, right? So shipping and aviation sector, how it look like, and uh, what is the hydrogen and how it's been manufactured, right? Proposed adaptation of hydrogen manufacturing process to Sri Lanka, advantages in modern hydrogen plant establishment and challenges in hydrogen storage, right? So those are the main highlights I would like to see. So if you see in world scenario, this is the energy usage, the roads. Fuel oil, the 49% is used on the vehicles on the road, right? The aviation sector use 8.3, then this is the shipping sector, so 6.8, right? So I wanted to highlight these two on this session because even our country is not ready with hydrogen. There will be ships coming to our ports with hydrogen equipment, right? There, there will be aeroplane coming to our airports with hydrogen. If we don't have those things in our ports, right, our dominance or our, the location preference will be loose and we will lose a lot as a country, right? So that's why we have to consider these two as a first requirement of meeting the needs of hydrogen, right? So other parts of the world will not wait until we develop, right? We have to provide them. It's like we are having our bunkering fuel in the ports, right? So we have to provide those things. I will tell you on the lecture why we have to keep this also for the ships. So you can see the world fuel prices, right? So right now you can see per liter, right? So it is settling in like 1.2, around 0.8 to 1.2, somewhere around that per liter, right? So even with hydrogen use, so it's going to $4 maximum. If you divide by the energy content, it would be on this range, right? So hydrogen would be also playing on that range. So the fossil fuel price will have a good competition with hydrogen. And this is the Europe currently hydrogen paying prices. You can see $2.92, right? Because hydrogen, you can see, this is the actual data, which I got it from USA on my visit, right? So you can see these are the values they are paying, right? This is the trend I told you, right? So hydrogen would be much cheaper than the diesel and petrol in near future, right? So that would be the driving factor, will enable the shipping industry or anybody to use hydrogen, right? So then the demand for hydrogen, right? These years, the COVID and all these things, there were not much requirement, but with the prediction, we expect 179, almost 180 million tons of hydrogen for the transport and these sectors, right? So bridging this gap from 2021 to this one, it's a very huge task. So this is how world has to see how we can do it, right? So you can see the current hydrogen usage. Even China is leading there, right? So they are using 29, right? So North America 17, Middle East 13. So these are the current hydrogen usage in the world, right? So this is net zero condition 2030. They will expect more usage on the other areas, right? And these are the current ongoing hydrogen projects around the world. Unfortunately, in our dot, we don't have anything, right? So you can see Europe, how much projects, right? You can see early stage, right? Operational. So you can see how many units operational in the world. This is a world hydrogen generation map, right? So how many countries had go into hydrogen and where we are. We have to, this is very alarming, right? So we have to be very quickly pick up and go in this direction. If not, we will have to buy hydrogen from other countries, right? So then I will go into the world shipping industry. So you might know, right? Currently, 90% of the okay.
So they can't see the slides.
You can sharing again.
It's not showing here. No, I'll call someone.
You call
Yeah.
maybe. Okay. Yeah. So right now, the 90% of the world trade happen through shipping, right? So per day, 20 million containers travel across the ocean. If you line up, it's half of the, the size of the earth, right? So container stretch the half around the world, right? So that much containers are, traveled around the world. A container ship travel enormous distance across the ocean every year. Not about one day we are talking about. So it's a very, considerable distance they are traveling. So you take the shipping routes, right? The darker lines are the core routes. Secondary routes are the thinner lines, right? So you can see, right here, the Sri Lanka, fortunately, we are there, right? So we have one of the dominant port in the world, right? So if we don't have the hydrogen here, right? So somebody will else grab that one, right? So that's why in the global context, we have to have our hydrogen storage here. There are some other reasons also, but we have to see this is the main reason our port is very, very important. And our port is having the most highest natural depth. That's a different thing, right? But main thing is we are in transition path. So we have very significant, the dominance on the location, right? So this is the carbon dioxide emission, right? From the shipping industry, you can see how it's going up. So that's why people are looking at different energy source, how we can reduce this fuel, carbon dioxide emission. This is the International Maritime Organization prediction. They wanted to go into zero emission by 2100, right? So you can see the drastic change they are planning, right? So these changes, they are planning with hydrogen, ammonia, and many other fuel sources, right? So that is, they had committed on this one, 2030 margins, 2050 margins, they had committed on that one, and it is very important for them to have this one, right? So, you can see on maritime fuel, right? The greenhouse gas emissions, right? You can see this is the HFO, heavy fuel, marine oil, then the LNG, the green hydrogen, then green hydrogen using fuel cells, right? So what are the environmental impacts you can see, right? Not present. These carbon dioxide, those things, right? If it is generated from wind farms and solar, okay, there are certain amounts, right? Because for manufacturing of plants, you require certain amount of carbon. So that's why it is, orange color. But generally, it would be very, clean fuel, right? So if we take a powertrain of a ship, right, with a hydrogen, you can see there's a storage, liquid hydrogen storage tank, right, and the fuel pump. And this is again a gasification process where the liquid hydrogen would gas and then feed into the engine and go into the power generation or the drive. So this is the Wärtsilä, one of the major shipping industry built their hydrogen engine, right? So you can see everything is already being finalized, right? So this is the ship development for coming years. So first one, Himson, so 2024, it is from hydrogen, sorry, ammonia. Then 2026, 2027, there are two hydrogen models coming, Kawasaki and Himsen, right? So it will be coming onto the ships, right? You can see how it's been developed, right? So ammonia, hydrogen, methanol, so they are using all the fuels. So these are the cycles, right? Cycle of operation. So these are the plan for, the upcoming mechanical driven system into the shipping industry, right? So you can see, so engines being developed, so we have to be ready with our fuel, right? So if I go to aviation industry, so this is a COVID patch, you can see, but again, it is on a rise. You can see 2050, right? How much increase we are looking at, right? So aviation industry would be another area where the highest carbon dioxide, right? You can see how much, right? By 2020, it's about 1 billion, right? Tons of carbon dioxide. Fortunately, right now they had started the hydrogen powered turboprop engine testing, right? And Airbus had started their gas turbine testing. And this is actually how it's fixed, right? So it is not sacrificing any safety. It's running with the main engine. This is being tested while the other engines are running, right? So other thing is, as the hydrogen infrastructure is not built, right? They are developing with the pods, hydrogen pods, where you can just plug in, right? So you don't have to build your infrastructure, piping network or anything. It is like your luggage. It will fit onto the cargo chamber of aircraft. You can just plug in this gas and you can run it, right? So as a country, we have to look on to something like that because we don't have a capital expenditure to put all the pipeline and do, but we can have our hydrogen system and make hydrogen pods of this nature, right? Where we can fit and we can give it to the ships, right? So this kind of, this is like again, a containerized thing, right? Like we have our trade, we have pod like this where we can fill it and send it. So this will be available very soon for all the countries where when they have hydrogen, they can fill it and put it, right? So this is the hydrogen power aviation trends, right? You can see they had test this one, 9 to 19 seaters, 27. These are the commercial operation dates. So they had already tested, so they will be in commercial operation. These, you can see 100 seaters, then the 200 seats and 200 plus seats, right? So these are the aircraft development plan for the future in the world, right? So we have to see how our fuel supply trend is matching with this one, right? So not like our Colombo port, our airport is not that nature because generally air travel will depend on the business clients, right? We don't have much industry where the business travels are coming. It's only the tourists are coming, but this is as per Sri Lankan Airlines, we serve this much of routes, right? So there are number of aircrafts coming. So there will be some would be having requirement of hydrogen, right? So we had discussed the requirement of hydrogen in aviation and naval industry. So we have to see how we can make it. So in the world, there are 4 main processes. One is electrolysis, then the thermochemical process, and third one is direct solar water splitting and biological processes. So those are the main processes where we can use for hydrogen manufacturing. So electrolyzers, so I initially showed you the simple thing, but you can see with the energy balance how it's coming, right? So this is how it's happened, but actually right now it is happening on this scale, right? It's called PEM, right? It's a proton electrolyte membrane electrolysis, right? So this is the membrane. So when we are making hydrogen, we were putting salt, right? You can't put salt when it is come to the commercial operation, it will deposit on the electrodes, right? So that's why, so they are using this membrane. So it's a polymer membrane, right? So it allows the proton to be moved, and I will show you little video on that one, right? So you can you might be able to see, this is the Bosch, right? PEM electrolysis system, but this is a commercial scale. I will show into more detailed one later, right? So this is called the hydrogen stack. They don't call it hydrogen electrolysis unit, called stack, right? So this is basically so I will go into more detail one. You can see on this one how the system works, right?
Configuration reduces construction and installation costs because much of the process equipment is pre-integrated before arriving on site. PEM electrolyzers are a mature and proven technology.
Yeah. Yeah.
Using only potable water and electricity as
Yeah.
The containerized configuration reduces construction and installation costs because much of the process equipment is pre-integrated before arriving on site. PEM electrolyzers are a mature and proven technology using only potable water and electricity as process inputs. NEL's PEM electrolyzer system design operates at full differential pressure, hydrogen over oxygen, essentially eliminating the hazard of oxygen entering the hydrogen stream. Water, purified by a reverse osmosis deionization unit, enters the cell stack and divides within the inlet manifold to feed each electrolysis cell. As DC current is applied to the bus connections, a small fraction of the water flowing through each cell is drawn to the cell anode and split into oxygen ions and protons. Oxygen gas bubbles then form at the anode and are forced into the bulk flow stream. The water and oxygen management system circulates water through the cell stack to be consumed via electrolysis, removes heat from the cell stack to maintain the proper temperature, and removes the oxygen gas that is generated in each of the cells. Simultaneously, hydrogen is transported from the cathode side of the cell to the hydrogen management system. There, the hydrogen phase separator separates the liquid protonic water from the hydrogen gas. The hydrogen gas leaves the separator and is cooled to condense water vapor from the hydrogen gas stream. The separated water is then transported to the water management system and is reclaimed into the water circulation loop. Hydrogen gas pressure is regulated in the gas management system to create a full differential pressure, hydrogen over oxygen, in the cell stack to prevent oxygen from entering the hydrogen stream. After the hydrogen gas leaves the hydrogen management system, the purity is greater than 99.9%. The hydrogen dryer module is an option for processes that require gas dew points as low as -65 degrees Celsius. The hydrogen gas purity at the outlet of the dryer module is greater than 99.9995% or less than 5 ppm water vapor. A safety-regulated PLC is
Okay. So now it is not the general electrolysis we see, right? So okay. So this is about HMI. But anyway, what I would like to highlight is current electrolyzers are coming in a stack where you have number of plates, you have the electrodes and the membrane in it, so that once you put the water and the power supply, the DC supply, it will generate the hydrogen. And also for hydrogen, the main culprit is oxygen, right? When you have the oxygen, it can burn, it can explode, right? So you have to remove the oxygen. So that's a very important part in safety. So that's why they are going into water phase separation and the dryer and going into that much, the purity of hydrogen, right? So Then the thermochemical processes. So we had learned about the electrolysis. So these are the chemical processes, right? There we use chemical process to break the get the hydrogen out, right? So about 99% of the world hydrogen right now is manufactured using steam reformer. It's not the electrolysis, right? So also this methane, they are coming from the natural gas, that is from the, fossil fuel sources, right? So they use steam and generate where the hydrogen is used right now. When you take any rockets out to the space, so they have the brown tank that is called the hydrogen tank. So it is used on rockets and even current hydrogen vehicles and other industries, they are using it, right? So there what will happen is steam reformer technology, you react the CH4 methane with H2O, steam, right? So these H2 will contact with this one. So 3 hydrogen molecules are created and the carbon monoxide. This is very, very unstable. This is very, very unstable. Yeah. So, so carbon monoxide is a very unstable element. So it always try to become carbon dioxide, which is a natural form, you can see. So when the water is present, it will grab the oxygen of that one. It become carbon dioxide and make the another hydrogen. So steam reformer technology is the technology that generate highest density of hydrogen in any process. When you take electrolysis, you get 1 hydrogen and half oxygen, right? But here you get 4 hydrogen, carbon dioxide, right? So that is the advantage of this one. You can get very high density of hydrogen. So and there you have to see the temperatures. The temperature of 1300 Fahrenheit, right? So they are operating at a very high temperatures to achieve that one, right? And this is biomethane plant, right? So that means if you have the biodegradable, this system, this containerized system can generate methane, right? So this is a hydrogen unit, right? So it is not a very big technology. You can have 2 container units, you can run a system, right? So when you have the biodegradable, you can run with that one. You can see the small, it about 5 to 120 normal meter cubes per hour, you can generate at 20 bar. So the power consumption is less than 40 kilowatts. So this is very efficient thing. So I want Sri Lanka to try this kind of thing. We don't want a very big plant, right? We have to have maybe modular technology. Try on this one. We will see with our garbage, our municipal solid waste, right? So this is basically from MSW, municipal solid waste, right? So we can collect our municipal solid waste and we can process it here, generate methane, and then that methane can be fed into this one and generate our requirement of hydrogen, right? So as a country, we should start at a small step, right? So there's a thermocatalytic process, right? So there you can see electrolyzers use about 50 to 55 kilowatt hour to generate 1 kg of hydrogen. You can see on this one, steam reformer, it's use about 60 to 10 kilowatt, right? You can see that's the advantage. That's why the hydrogen cost is coming down. It's about $2.72 per kilogram, right? So you can see, and also the carbon dioxide emission, right? You can see for 1 kg of hydrogen, you have 3 kg of carbon, right? So when you have the catalytic one, you can reduce this steam reformer 9 kg again, you can reduce, right? So then I will come to biomass. So we had talked about steam reformer. This is biomass, right? So even on gasification, when you have the biomass, you can gasify biomass. So this is a gasification reaction. You can see carbon reaction with oxygen. So they generate about 25 to 30% of hydrogen, right? So you don't have to go for like very high technology, right? This is actually my design operating in Sri Lanka, right? So that this is a hydrogen plant. So the biggest advantage there is that you have a carbon sink there. 40% carbon is stored there, right? So I will show it to you. So this is the first experimental unit I had done with a few of our engineers. So you could see you could check the color of the flame here, right? So it is, you will see it is coming white. This white area are the hydrogen part, right? And you can see this is a local design process where the biomass is converted into this one. With hydrogen, you can see this white color. And I'm sorry about the noise because when I'm recording, it was doing sound. Right? So you can see it's a continuous gas coming out, right? So when you have the correct oxygen level, this flame cannot be seen, right? So this is without much oxygen mixing, right? So this is actual level. You can see the smoke coming, but you don't see the flame there, right? So that's the biggest danger in hydrogen, where you have an invisible flame. You never know until you catch fire. When your clothes or anything burn, you can see because it's becoming yellow, right? When they are burning. But hydrogen, when it's burning, it's an invisible flame. This is today morning our operation, right? You can see it's very less color, right? So that system is generating hydrogen and carbon monoxide. It's burning there, right? Anyway, Parakrama had done this one about 40 years before me, right? But I'm telling, this is another technology that we can do in our country to generate hydrogen, right? So generally, these kind of plants has been there from commercial scale. I think from 2000, no sir. So Kandalama Hotel is having one gasifier. TW Mackey Horan is having one gasifier. Tea Factory Hotel. So all this I had involvement and we are doing. So right now I'm trying to see whether I could give the technology for some of the industries to convert from fossil fuel to this type of our own fuel sources. So direct solar water splitting, right? This is one good area you might have not seen. This is, I had seen USA. So like the solar panel, these panels would be mounted on your roof, right? So when the solar radiation comes, it generates hydrogen. So you have to feed this one. The unit is like this. You can see. So this is with a enzyme, right? The only problem with that one, when I was in that exhibition, this enzyme could last long only 43 days. You have to change the enzyme every 43 days. So they are looking at, they're improving the lifetime of this enzyme, how they can do this one. So the Biomax is the company that was doing. So this is at actually USA. So you can see the gas collection is happening here, right? So they would be, I will be going back. So you can see it is mounted on a maybe rooftop. It's like your maybe one side of your roof can be solar, one side of your this thing can be hydrogen generating unit, right? So you can have your full independence on energy from the any other sources. You can generate your own system, right? So this is light activated. You can store it and put it, right? So you can see how many techniques available to generate hydrogen. We were looking at only electrolysis. I hope I bring you something that you have not seen, where we can go into different areas of generating hydrogen, right? So potential sources for Sri Lanka, I would say steam reformer using municipal solid waste we can do, and even electrolysis, right? So not to a very big scale, but we can start on that one as a, then the gasification, right? Those three techniques we can see. I am not talking about the enzyme type because it is still on the experimental phase. So it will be commercialized pretty soon. So without petroleum reserve, how Sri Lanka could generate methane, right? So Sri Lanka in Colombo, Western province only, we generate 300 metric tons of biodegradable every day, right? So it is enough to generate 2 metric tons of methane per day, right? This could produce about 2 tons of hydrogen, right? So, with the other sources, we would be able to increase it to 10 metric tons, right? Because this is Western province only. If we take all the provinces, we can go into 10 metric ton, right? So we can start those things. So I will show you, right? This is the municipal solid waste. This is how much methane is generated. Right now, Sri Lanka is producing about 7,000 metric tons of municipal solid waste every day. So out of that, 53% is biodegradable. So 7,000 means 3,500. We have this much. You can see how much methane we can generate, right? So if we use our biodegradable or the municipal solid waste, we can generate more and more hydrogen into the system, right? So you can see how much kilogram of methane also can be generated. So this is for anybody who would like to research into this area. So all the information I had given, and I'm more than happy to support anybody who would like to have more information. So the conversion process of methane to hydrogen, you can see how much water required, the energy, and the natural gas. So you could get 1 kg of hydrogen on that one, right? And future hydrogen storage terminal would look like this. So you can see in airport, right? So in ports also, when we have our hydrogen, so we should have the hydrogen storage hubs like this, right? So, but we talk about the good story, right? So the, the best side of hydrogen. But there are many challenges as engineers we have to take on hydrogen, right? So I would like to touch on those areas also. First thing is for the electrolysis, the water quality requirement. You have to see, right? This is lab scale water, sorry. Right? You can see the chlorine level, right? This chlorine level, right? You can see the sodium, the silica, right? You can see how much purity of water we require in this electrolysis, right? Because if not, they will deposits on the electrolytes, right? So this is the most challenging part. It's very easy to talk about the fairy tale about generating hydrogen, but generating this water is more difficult than making hydrogen, right? So you have to see on that part. That's why I wanted to highlight this one, right? So it is not easy. You can't just take a RO system, reverse osmosis system, and generate water, right? There are polishing and many things to be done. You can see the requirement, right? So it is the most challenging thing in electrolyzers we have to do. So I think we have to take them. We have to remove iron, particle, organics, bacteria, because everything will deposit and your performance will go down in no time, right? Second thing is hydrogen storage temperature. You can see hydrogen has to store, sorry, it's minus 253, right? Hydrogen will be liquefied at this temperature. So this is like almost absolute zero, right? 275 is absolute zero. So we are almost close to absolute zero, right? So keeping hydrogen on this temperature without heat being dissipated out, that would be the again challenge. This is called cryogenic, right? The cryogenic word generate from, actually it is from history where it came if somebody is sick. You imagine like a pharaohs in Egypt, right? If they sick, right? They wanted to keep the person freeze until the medicine is found. So that's why the cryogenic word came, right? So that temperature is used to, hibernate people, right? So that's why this one came. So this is like a cryogenic temperatures we have to use. So keeping that temperature in this one would be very difficult. You can see hydrogen evaporate at 252. So if you the temperature increases, liquid hydrogen will become gaseous and create more pressure in the system. So that is very, very difficult task. So you can see the helium is the most challenging, but hydrogen would be on the third on the list, right? So that is a very, very difficult thing. And other one would be the hydrogen leakage. This is called Hindenburg disaster, May 16, 1937, right? So the hydrogen had been used before us, right? 1937 for air travel, for air balloons, right? So there was a small leak. You can see in no time it burned, and all the crew, 61 crew and the 36 passengers were died on spot, right? They were burned on sky, right? So this much of danger we are talking about, right? So that hydrogen leakage would be very, very lethal and very difficult thing. But as I told you, there are storage has been built with carbon fiber where even, sniper bullet cannot penetrate. So there are many things that come, but still as a Sri Lankan, if we are building, right, we have a lot of challenges to do, right? So that's very, very difficult part. Then the compressors. Actually, this is these compressors already being done because the LNG, liquid natural gas compressors are available on the world. For the hydrogen, it need to be, stored at a pressure of 350 to 700 bars. So you can imagine, I think Engineer Jans would see the boilers, we never talk about 120, 160, right? So you can see about 700 bar pressure system, right? So it is unbelievable pressures we have to work with, right? On liquid phase, right? So reciprocating and the centrifugal, we can reach those areas. So easily the technology is available, right? But I will tell you there are challenges on it, right? So the capital cost. Right now, the capital cost for 1 kilowatt is on the range of 1,500, but we expect it to come down to 500, right? So these are the trends. So until the trend is come to that one, it would be sometime unaffordable for countries like us, right? But we have to see that part separately. And the other one is storage space, right? Because for a ship or aircraft, the space is very precious for them. For passengers and the cargo, they keep it. You can see marine grade oil, if it is require 1, hydrogen, it require more than 4.5 volume, right? So if it is 1,000 meter cube one, they require 4,500 meter cube space, right? So that is a challenging part, especially on ships also, right? You can see this is very, very difficult. That's why I told you why. I will tell you why we require hydrogen. No ship will carry fuel from one port to the end port. They will require refueling in mid port, right? Because they can't carry all the fuel because they require a lot of space on the ship, right? If they keep that one, they can't carry the goods, right? So and they are like sitting on a a very dangerous bomb, right? So they will always go for like minimum volume, right? Which will make their cargoes economical. So that's why we require that one. So this is again challenge, right? Even at 700 bar at minus 253, we have this value, right? So you can see the challenges we are facing on the usage of hydrogen as a fuel, right? So this is the fuel pump that I told you. The fuel pump is the greatest challenge in this hydrogen industry. If I tell you why, right? If it is a car, right? When your fuel pump is maybe at a 30 degrees Celsius and minus 253 coming, all your seals will not be there. At that temperature, everything will shrink, right? So you will not be able to maintain that one, right? So that is the most challenging part in the hydrogen industry. How you maintain such temperature difference, right? Where once it is start pumping, you will get a super cool liquid going through your system. But when it is not running, you will be at atmospheric temperature, right? So that it's a very, very challenging thing, right? So they have to have different technologies like pre-cooling systems to get the system, by stage, just like the boilers. We never pressurized to the full pressure initially, right? We will do it on a stages. So there are many systems developing on that one. So this is one of the greater challenge we have on hydrogen part. And challenges on hydrogen, the material, right? This is again, like the pump, this is one of the biggest thing. That's why I want to put a special slide before I go into this one. You can see even the gas, many material are acceptable. For liquid, is not acceptable. Right? You can see gray ductile iron, low alloy steel, right? Nickel, cadmium, right? Nickel steel, titanium is acceptable. But you can see how many material we can't use for liquid phase, right? So we might have to invent new material for that one, right? So that is again a very, very challenging situation for hydrogen industry, where we have to develop different methodology. You know all the mechanical engineers, the hydrogen embrittlement in welding, right? So how it can create so much strength failures and problems, right? So it is associated with this one. So the material challenge is the next major challenge we have on that one. That's why people had gone for reinforced carbon fiber. So that technology is developing. So we hope we will be able to see good material coming on this one. And so other challenges would be like large scale production. As I told you, there can be a lot of risk associated with it. Technology and infrastructure limitation, safety consideration, supply and demand uncertainties, lack of policy initiatives of government. So you can see these are the other challenges we have to see. Despite many challenges, still hydrogen is picking up because it has so much financial value on it, right? And environmental value on it, right? So that's why as a country, even though it is challenging, we have to see, we don't have to go for maybe high pressures. Let's use it on an atmosphere, or maybe at a certain level we can use it, right? So, so this is, you can see, this is 5 university students from USA. They had developed the hydrogen bike. So I wanted to put them to appreciate their effort, right? So while whole world is doing research, these kind of students are there. They would like to touch on this one. So there's a canister you might see here. So it's like a canister type. You have to plug in the canister. It can go up to 70 miles. So after that, they have to change the canister and go. It's like you're having your own LPG cylinder, just plugging it and moving. So they had developed this one, and it's running through fuel cell technology, generating the electricity and operating this one. So it's a Kawasaki bike, right? So they had already going into this one. So these all are gaseous, right? You have to see this is not liquid hydrogen storage, right? Because we will have problem if we have the pumps there. So we can't have pumps there. So it will be running on gaseous, right? And, you know, these are called high bypass engines, right? So only the fighter jets have the low bypass where the 100% air go through, but these are called high bypass engines where it is used on aircraft industry. So the main problem they had was generating the combustion chamber. On the other gas turbines, we have individual there are 24 and 36 annulus, like not annulus, it's like a compartment like combustion chambers where you can fuel inject it. But for hydrogen, they had developed annulus type thing, so that they are planning, these are the storage tank they are looking at. So these are the development of hydrogen. Despite the challenges, they are making all the effort to make it hydrogen more feasible. You can see now you can buy containerized unit like this fuel cell. You can see it's 6.4 megawatt capacity, right? So you have 3.2 megawatt capacity. So it is available in the market where you can buy this one, right? So that if you have the hydrogen, you can get this one and run and get the power requirement you require, right? So what Sri Lanka need in getting hydrogen ready by 2030, right? So first one is a policy directive, right? To authorize construction. Even we have certain hydrogen projects in Sri Lanka where we find it's very difficult to get the policy decisions aligned with this requirement of hydrogen, because I feel we should not go into very bigger one, but we should start with something to get to know, right? For example, Dendro, the biomass plant started with Valapane. Even everybody blame for Valapane, that was the learning point, right? Where we learn everything about biomass. Then we were operate all, now you can see all the industries running on biomass boilers, right? So we were running on this one. So we require something to move ahead. So we require policy directives to be aligned with the hydrogen future, right? So you can see the cooperation between governments, right? Unfortunately, Sri Lanka is not there, right? So we require right now. The company that I'm working with, they are ready to come, Italian company, but we still trying to get the policy directive aligned to get into this one, where we can have some sort of agreement on and move on to this one, right? Next requirement we have to do, we have to get cooperation between the other government and get something going ahead. Another one is we cry for bigger plants. Let's start with this kind of unit, right? Smaller unit. So we will go with containerized units, and we will see maybe from Pradesh Sabha to Pradesh Sabha, maybe from district to district. Let's start some centers, right? Let's give some energy. Let's generate, first we can generate methane and sell it to the people. We don't have to make hydrogen, right? The methane is good fuel where we can sell it to any place. Methane is nothing but LNG. It's not liquefied. It's LNG is when it is liquefied, but all the LNG, even we use LPG at home at a gaseous phase. So liquid gas will be vaporized and used, but we can have our system going, generating methane as a modular construction where as a starting point. Then when we have the generation points going, we can have the second module coming in, plugging it, right? So that I would like to go on this case where we can see, for example, even for Colombo, we can put some container and give to the recently planning to commission LNG power plant, because it is done for LNG, right? So even that LNG is, gasified before it been used. So they can easily use this one. So we have to see on that part how we can get this one going, right? So this is on Denmark, how they had planned their port infrastructure. You can see the pipe network, everything. So they are getting the power from wind turbines and things like that, right? We might not be able to have all these things, but we should have at least some hydrogen storage tank in the port, and we should be able to refuel our ships, right? So that infrastructure has to be built to meet the challenges of the future vessels coming into the Sri Lankan ports. And I told you initially, you can see the engine development. So there are technological development coming in 2025, 2020. The aircraft development up to 2040. So we have to have our plan aligned with these one, right? It is not that we have our plan, because I will show you our plan, the Sri Lankan plan, right? So we are planning to have one 2035, this range, right? You can see. So these are the policy directive, but I haven't seen it is coming, right? So this is the Sri Lankan hydrogen plan, right? So we need to expedite these things and getting on, right? So how realistic and how updated these things, we have to check and see as a country how we can get into the market, because with the hydrogen, we will be able to at least reduce 1% of the fossil fuel use. That would generate certain amount. That means a lot of foreign exchange saving, right?
Thank you so much for your questions. That's all the time we have for tonight. There was a comprehensive and informative lecture on the manufacturing process, the challenges, the demand and feasibility within the aviation, transport, and marine sectors of the most abundant element in the universe, done by engineer Ruan Nagawata. Thank you, sir, for the time and the energy you put into the presentation here today. Now I'd like to cordially invite Engineer Kasunta from the Mechanical Engineering Sectional Committee to deliver the vote of thanks.
So good evening, everyone. I think you all have enjoyed a very fruitful lecture all about hydrogen technology, but we haven't touched up now. So I think this evening is most interesting because Engineer Ruan Nagahata, one of the distinguished engineers in our ISA, who is leading our mechanical engineering section committee, has given you thoughts and holistic overview about the hydrogen technology and green energy. Especially he's practicing that, he has shown how he's using that, and theoretically, practically, and in the terms of economic terms. So I must pay my gratitude for the engineer Ruan Nagawatha, chairman, mechanical engineering section committee. In the last moment, we invited him for this lecture. I think within 1 week of time, we were able to arrange this one. And I'm really thankful for you for this valuable lecture and valuable insights. I think all of you have got the answers for all the questions, and really thankful for that. And I must thank for the ISL staff and all the people behind this big stage, because I must remember them, because without them we can't have this kind of a big lecture. So Chamila and his team and all the people from ISL who have given their biggest support on behalf of this lecture. And I must remember all the engineers, mechanical engineers who are in our mechanical engineering section committee who have given the biggest support for this event. The senior engineers especially who are assisting us in each and everything what we are doing. So I must remember all of them, as well as all the mechanical engineering section committee members for their massive support. And finally, I would like to thank you all for being here and investing your valuable time on behalf of this fruitful lecture in this evening. So thank you very much for being here with us, the physical participants, as well as all the online participants who are being with us, spending their valuable time and getting something out of the thing what we have done. So thank you everyone who are being with us and who have helped for us to make this success. Thank you.